Hello, welcome back to POE. The other piece of the puzzle here with fluid power is hydraulic power. And hydraulic power uses a liquid. Typically it's an oil of some sort. And the liquids are not compressible. So when you push one end a little bit, something moves down on the other end a little bit, assuming it can, otherwise the pressure just builds up. So when you push something else moves. So hydraulic power is used on most of what you're going to see in heavy machinery, and they use hydraulic pistons. So this is a zoomed in picture of the of what lifts the ladder. So this is a hydraulic piston which extends when the fluid is sent to it. You can see these are hydraulic lines that go to it. These are stabilizer pods, which just make the extend the area of the base of support, and these get put out with these hydraulic pistons when they're going to lift the ladder, and they need to make sure that they're stable. So the difference between this and a pneumatic system, hydraulic systems use a liquid, typically an oil, which doesn't really compress. They're slower and smoother in their motion as opposed to the jerkier pneumatic or gas-powered devices. They're more precise since they're slower and smoother. You do not need another lubricant because they use an oil to begin with. They do make a mess when there's a leak. There's a hydraulic fluid leaks all over the place. You got a problem. They operate at higher pressures and generally produce more power than pneumatic systems. So here's an example of an early hydraulic use water wheel. So kind of a cool old-timey picture. The water turned the wheel, and the wheel turned some type of mill. In this case, a big stone. Here we've got the aqueducts. Again, I think these are kind of a little bit goofy examples, but okay. So here we've got a propeller, which might have been used to convert the motion of water into spinning motion, which would be converted into electricity. That kind of thing. So in a hydrostatic, hydro meaning water or liquid, static meaning not moving. In hydrostatic systems, the fluid is at rest and it's pressurized, and the pressure creates force and energy when it moves. This is pretty common in industrial settings. So the first thing we're going to look at is flow rate. So the flow rate is the volume of the liquid that moves through a system in a given amount of time. The velocity is basically the speed of a particular molecule as it flows down the pipe at a given period of time. A little chunk of fluid, the speed of it. So that's the flow velocity. So Q is representing flow rate. It doesn't mean heat in this case. So when you're talking about fluids, Q is not heat, it's flow rate. V is the flow velocity, and A is the area, and Q equals V times A. So when you multiply your flow velocity times the area, and this is the cross-sectional area of the pipe that it's talking about, then you get the flow rate in inches cubed per minute. So we got to make sure that our area is in inches squared and our flow velocity is in inches per minute, and we want to make sure that our flow volume, our flow rate, is in inches cubed per minute. So here, this is a really common flow meter that I used to see all the time back when I was in industry. You've got this tapering sort of inside, and the faster the water would flow, the higher the ball would float, and you would just read the flow rate off the ball. So here we've got a flow meter in a hydraulic system. The flow rate is 15 gallons per minute. The line has an inside velocity of 2 inches. What is the flow velocity in the meter? Okay. So we've got our flow rate is in gallons per minute. Now we don't want that in gallons per minute. We want that in inches per minute, or inches cubed per minute. We've got our diameter, which we want to convert to area, and we're looking for the flow velocity. So the first thing we do is convert gallons per minute into inches per minute, inches cubed per minute. So what I would do is next to this equation, which is by all the other equations we've been using, write that 1 gallon equals 231 cubic inches. Take a second and do that, and then that way you've got that handy to where you would be using it. So we're in the equations in the 9.1 something, I think. So anyway, we get our 15 gallons per minute. Okay, pause it if you need to. We convert our 1 gallon is 231 cubic inches. So we get that our flow rate is equal to 3465 inches cubed per minute. So that's step 1. The next step is to figure out the inside cross-sectional area of the pipe. Okay, we're given that it has an inside diameter of 2 inches. Okay, so we need to convert that into the area of the circle of the pipe, because the pipe has a circular inside. So we'll use A equals pi r squared. So the diameter is 2, but this calls for the radius, not the diameter. So it's pi times 1 squared. So the final area is 3.14 inches squared. Okay, then finally we use our equation. Q equals VA. So Q we just solved on the previous page was 3465. Okay. Our V is what we're looking for, the flow velocity, and we just found the area. It was 3.14. So we take both sides and divide by 3.14. Okay, and we get 1100 inches per minute. That is the flow velocity. Okay, any questions? I didn't think so. Alright, hydrostatic systems. So basically they follow Pascal's law, which is what we talked about the other day. Pressure equals force over area. Oh, click on the arrows to activate them. That almost goes together. Huh. That's funny. I didn't know you could do button activated things. Huh. Anyway, so pressure equals force over area. So basically, when I push down on this big piston, okay, I get a lot of linear motion on this piston over here. When I push down on this piston, I don't get as much motion, okay, but I get a lot more force. So that kind of reminds me of levers in simple machines. There's a trade-off between force and distance, and that is the exact same trade-off with the hydraulic system. So, if you weren't picturing these are pipes connected by a pipe, and this is a larger diameter piston and connected to a smaller diameter piston. Anyway, so we all remember mechanical advantage, but first let's solve this problem. So this is a better picture of what we were seeing on the previous page. It just doesn't move. So what we're going to do is we're going to apply 100 pounds of force onto a piston with a diameter of 4 inches. Okay, and then that's going to squeeze down on this piston. It's going to push up on this piston, and this piston has a diameter of 12 inches, and we want to know what's the force acting on it. So when we squeeze down with this, we're going to push this a long way, and this is only going to go up a little bit. So we're losing distance, and when we lose distance, typically the trade-off is that we gain force. So we should end up with extra force on the output. So the first thing we're going to do is we're going to figure out the pressure that we're applying to this piston here, or the pressure that this piston is applying to the fluid. and we're going to say that pressure is equal to the pressure that's being applied to this piston. Okay, and then we'll solve for the force for that. Okay. So find the area of each cylinder. So we've got a radius. The one was 4 inches diameter, so it's a radius of 2, and the other one has a diameter of 12, so it's got a radius of 6. Use pi r squared, and just find the radius of the input and output piston. So the area of the input piston is pi times 4 squared, so 13 inches squared. So this one is 13 square inches. And this one, pi 6 squared, this is 110 square inches. Okay, so 13 square inches and 110 square inches. So we have a lot more area on the bigger piston. The next thing we need to do is find the pressure in the system. So we're going to look at, okay, I applied 100 pounds of force to 12.57 square inches. Okay, so that's I'm going to find the pressure. So pressure equals force, 100 pounds, divided by the area, which is 12.57 square inches. Okay, and we've got a pressure of roughly 8.0 pounds per square inch. So that's the pressure that's being applied to this fluid here, which is the same as the pressure that's going to be applied to this bigger piston here. Okay, so now we're going to figure out how much force is actually on this piston. So we know the pressure on the big piston is equal to the 7.955, so roughly 8, just like on the previous slide. They gave us an answer of 8.0. That equals the output force over the area of the piston, the output piston. So multiply through by 113, and we get that the output force is equal to basically 900 pounds. Okay. So we put in 100 pounds and we got out 900 pounds. So we gained force, but the trade-off was we lost distance. Okay. The mechanical advantage of the system, remember mechanical advantage, that equals the output force divided by the input force. The output force was 900 pounds, the input force was 100 pounds, so our mechanical advantage was 9. Bernoulli's principle, that's pretty much the meat and potatoes of it. This was just a couple other things to throw in here. So Bernoulli's principle basically says that when the fluid speeds up, the pressure it exerts decreases. So when the fluid goes into this restriction, it's going to speed up. It's going to increase speed because the area is going to go down, which is going to cause the velocity to go up. The pressure on these walls is actually going to be less than the pressure on these walls. Viscosity is basically how thick a fluid is. Water has a relatively low velocity, whereas honey has a much higher velocity, and that is important. Measured in slugs per second foot, or centistokes. Slugs is a unit of mass. It's funny. Typically, as the fluid increases, it gets warmer, the viscosity decreases. So some common components on a hydraulic system. We've got a reservoir. We've got transmission lines. We've got a filter. Again, typically you find filters on these systems too. You've got a pump, which is pressurizing the fluid, drawing the fluid from the reservoir, sending it to whatever that is. And then here we've got a valve, control valve, and here's an output cylinder. So I would use this valve to extend and retract this piston, and that sort of thing. So click on the lever on the valve and to restrict. Well, somebody must be proud of that animation. So this I never heard of before. This is a hydraulic vehicle. And basically, I looked it up. I didn't find too much information on it. I didn't try that hard, but it looks like it's another regenerative braking system, which basically means the energy that you normally would lose by applying your brakes and converting the energy into heat. That energy gets stored in a pressurized reservoir, and is available to when you speed up the next time. So this is 60 to 70% fuel economy, better fuel economy on a car that makes a lot of stops and starts, like a UPS vehicle. 40% reduction in CO2. I don't know why it wouldn't be 60 to 70% reduction in CO2 either, but whatever. Anyway, that is it for the day. Good luck. Hopefully that made some sense to you guys, and work on the paper.